In 2004, Google published a paper describing a programming model they'd been using internally to process petabytes of data for building their search index. The paper was called MapReduce, Simplified Data Processing on Large Clusters. In 2006, Hadoop and open-source implementation followed. Here's how the book describes it. MapReduce is a bit like Unix tools, but distributed across potentially thousands of machines. A single MapReduce job is comparable to a single Unix process. It takes one or more inputs and produces one or more outputs. The execution model follows 4 steps, and you've already seen all of them in the Unix pipeline. Step 1, read input files and break them into records. In our log example, each record is 1 line. Step 2, call the mapper function on each record to extract a key-value pair. This is the awk part, awk, print, extracted the URL as the key, with an empty value. Step 3, sort all key-value pairs by key. This is the implicit sort step. MapReduce does this automatically. You don't write it. Step 4, call the reducer function on each group of values sharing the same key. This is Unix C, it counts how many times each key appeared. The crucial difference from Unix is parallelism. MapReduce parallelizes across thousands of machines without you writing any threading code. The mapper and reducer only operate on one record at a time. They don't need to know where input comes from or where output goes. The framework handles movement of data between machines. In Hadoop, each input file is typically hundreds of megabytes. The scheduler tries to run each mapper on the machine that already stores a replica of that file, a principle called putting the computation near the data. This reduces network load. The process of partitioning mapper outputs by reducer, sorting, and copying them across the network is called the shuffle. And it's expensive. That cost drives everything we're about to discuss. Let me make the mechanics concrete. You have a Hadoop cluster. HDFS, the Hadoop Distributed File System, stores your data as blocks replicated across machines. HDFS is based on the shared nothing principle, no special hardware, just commodity machines connected over a data center network. At the time of writing, the biggest HDFS deployments run on tens of thousands of machines, with combined storage of hundreds of petabytes. A MapReduce job reads from an input directory in HDFS. Each file or file block is a separate partition, processed by a separate map task. Figure 10.1 shows 3 mappers and 3 reducers. Here's what happens inside the map phase. The framework copies your JAR file to the assigned machine, starts the map task, and reads the input file record by record, passing each to your mapper callback. The mapper outputs key-value pairs. These are written to a sorted file on the mapper's local disk, partitioned by which reducer will receive them using a hash of the key to decide. Then the shuffle begins. The reduced tasks connect to each mapper and download the sorted key-value files for their partition. The reduced task merges these files together, preserving sort order. Now all values for a given key are adjacent. The reducer receives a key and an iterator over all values for that key. It can produce any number of output records. These are written to a file on HDFS. One important detail, the number of reduced tasks is configured by you, the job author. It can be different from the number of map tasks. And here's the key insight about fault tolerance. MapReduce writes intermediate results to disk after every map and reduce stage. If a task fails, the framework just reruns it from the last write. That's why MapReduce is slower than the alternatives, but also why it can tolerate task failures in clusters where, at Google, a task running for an hour has approximately a 5% chance of being terminated by a higher priority process. Now let's talk about the hardest part of batch processing, joins. Here's the scenario from the book. You have 2 datasets living in HDFS. On the left, a log of user activity events, clickstream data, 1 record per user action, containing only a user ID. On the right, a user database with full profiles including date of birth. You want to know which pages are most popular with which age groups. So you need to join the activity events with the user profiles, find all events for user 104, look up user 104's date of birth, pair them together. The naive approach, for every activity event, query the user database over the network. That's disastrous for batch throughput. Round-trip latency to a database would dominate your running time. And running thousands of parallel mappers querying the same database would easily overwhelm it. The right approach, take a copy of the user database extracted via an ETL process and put it in HDFS alongside the activity events. Now MapReduce can bring the data together without any network lookups. This is a reduce side sort merge join. Here's how it works. 2 sets of mappers process the 2 input files independently. The activity event mappers emit user_ID activity_event. The user database mappers emit user_ID date_of_birth. Both use user_ID as the key. MapReduce sorts all key-value pairs by key and sends all pairs with the same key to the same reducer. The secondary sort technique ensures the user profile record arrives at the reducer first, followed by activity events in timestamp order. The reducer stores the date of birth in a local variable, then iterates over all the activity events, outputting viewed_URL, viewer_age_in_years, pairs. This is called a sort merge join. Mapper output is sorted by key, and reducers merge together the sorted lists of records from both sides of the join. It requires a full shuffle across the network, expensive, but completely general. The reduce side join is general but expensive. All that sorting, copying across the network, merging the data may be written to disk multiple times as it passes through the stages of MapReduce. Here's the setup for a faster approach. If you can make certain assumptions about your input data, you can skip the reducers entirely. The first case is the broadcast hash join. This applies when one dataset is small enough to fit entirely in memory. Imagine the user database is small, say, a few hundred megabytes. When each mapper starts, it reads the entire user database from HDFS into an in-memory hash table. Then it scans over the activity events and looks up each user ID in the hash table. No shuffle, no sort, no reducers. The word broadcast captures it perfectly. The small dataset is broadcast to all partitions of the large input. The word hash reflects the in-memory hash table. This join is supported by Pig under the name replicated join, by Hive under mapjoin, and by cascading in Crunch. It's also used in MPP query engines like Impala. The second case is the partition hash join called bucket map joins in Hive. This applies when both datasets are partitioned the same way. If both the activity events and the user database are partitioned based on the last decimal digit of user ID, giving 10 partitions on each side, then mapper 3 only needs to handle user IDs ending in 3. It loads those users into a hash table and processes only those activity events. Each mapper handles a smaller dataset than in the broadcast case. The third case is the map-side merge join. If both datasets are not only partitioned the same way but also sorted on the same key, no hash table is needed at all. The mapper reads both input files incrementally, in ascending key order, matching records with the same key, exactly what a reducer would do, but without the shuffle. Map-side joins are faster, but they require you to know the partitioning structure of your input data in advance.